In this video tutorial, we will use Sentinel-1 data to map urban footprints. We will do that using both the amplitude and the phase of the signal. We will use two Sentinel-1 images. We will calculate the amplitude, the calibrated amplitude for each image, and we'll also calculate the interferometric coherence between the two images. And we will use the amplitude and the coherence to mask out the urban areas. So let's get started. First, we will open the two Sentinel-1 images. So here we have the Sentinel-1 images in the Product Explorer window. We can see from the file name the acquisition dates. So one was acquired on the 2nd of January 2016, the other on the 26th of January. If we look at the bands, we can see that the images are complex. We have the complex bands, and we also have the virtual intensity band. The first thing we will do is to subset these images, because we do not need the whole image. So we go to Radar, Sentinel-1 Tops, Sentinel-1 Top Split. And here in Processing Parameters, here we can zoom in to the footprint of the image. And we can select the various different subswaths and the various different bursts. So we want to select IW1 and bursts 4 to 8. In the I/O parameters, we can select our output folder and the output file name. By default, it adds an underscore split to the end of the original file name, and we click on Run. I will do all the processing on one of the images, and then the processing again on the second image. And then finally, we will merge them together. So here we have our split product. The next thing we will do is to apply precise orbits. So we go to Radar, Apply Orbit File. We select the split product, and here under Processing Parameters we can select Do Not Fail if new orbit file is not found. The precise orbits will be downloaded automatically from the internet. If for any reason it does not work, then the process will not stop. So now we can select our output file name, and we can select Run. The precise orbits will give us better orbit information, which will improve the geometric correction and the co-registration. And the reason why we have to download this from the internet is because when the product was created, the precise orbits were not available. So now we will do a calibration. So notice how the bands we have at the moment are the complex bands, and we have an intensity band, which is a virtual band created on the fly. We will now calibrate this image to create a sigma naught, a band of sigma naught backscatter. So we go to Radar, Radiometric, Calibrate. And here we select the product with the precise orbits. And in the processing parameters, we will leave everything as default. So we will output a sigma naught band. And we click on Run. The next process is to perform a deburst. So here we have the calibrated sigma naught band. If we double click on that, we can view that in a viewer. The debursting will remove this space in between the various bursts. So it will stitch these together, and it will remove these no data values. So we go to radar, Sentinel-1 tops, deburst. And we can leave everything as default. Notice how it creates an underscore DEB for deburst. Okay, that's finished. It took 31 seconds. So here we have our debursted image. Okay, we no longer see those black lines in between the bursts. The next thing we will do is to do a multi-looking. So this image is in single look complex format. So the dimensions between the pixels in X and Y are not the same. So we will create square pixels by selecting radar, multi-looking. And in the processing parameters, we will leave the default multi-look factor to create square pixels, which in this case is 3 by range and 1 by azimuth. And we will select run. The multi-looking will also reduce the speckle by some degree, as it averages out some of the pixels in one dimension. So here we have our multi-looked image. We double click on that, we can see the result. Okay, so now we have square pixels. Notice how the histogram here is not so easy to manipulate. What we commonly do is to convert the band from linear to a logarithmic scale, and that will create a histogram that's much easier to work with. It improves the visualization of the image. So here we will create a new virtual band, which is in logarithmic scale, in decibels. So if we double click on that, here we have a histogram that's much easier to work with, and the image is easier to visualize. Finally, what we'll do is to geometrically correct the image. In fact, we will do a terrain correction that uses also a DEM to correct for the terrain. So we go to radar, geometric terrain correction, range Doppler terrain correction. And here in the processing parameters, we can leave everything as default. So we'll use the SRTM 3 arc second DEM, which will be downloaded automatically. We will keep the default pixel spacing and the default map projection. And we will check the input-output parameters, and then we will select run. The software will now look for the relevant DEM tile that covers this area, and if it does not find it in the relevant folder, then it will download it automatically from the internet. In this case, I already have the DEM tile, so it does not need to download it. So that's done. It was completed in 54 seconds. We can now close this window, and here we have our final terrain corrected product. We will again create a virtual band in decibels. And here we have our terrain corrected, calibrated, multi-looked image in decibels. So we will repeat all of these steps for the second image, which I will not do here in this video tutorial. Once we have done that, we'll have both of the images calibrated and terrain corrected. And what we'll do is to now create another image, which is the coherence image. So to do that, I'll close everything in my Product Explorer window. So to do that, I will open the two images that have already been split and already have precise orbits. So here we have one, and here we have the second. To calculate the coherence, first we need to co-register the two images, and then we can estimate the coherence. Once we have done that, we will do a TOPS deburst, a multi-looking, and a terrain correction of the coherence image. So first of all, to do a co-registration, we select radar, co-registration, Sentinel-1 TOPS co-registration, and we will select Sentinel-1 back geocoding. Here we can select this icon to add the images that are opened, and we will leave everything as default. What we'll do here though is to change the file name to leave only the common parts that are relevant to both images. So we will remove the acquisition date and various other information and leave only the common parts. Then we select Run. So the co-registration will resample one image onto the other. And this has to be done very precisely for proper calculation of the interferometric coherence. And the pixels from both images need to match to a very high precision, well below 1 pixel. Here we have our co-registered stack. We can now close this window. And the next step is to calculate the coherence. So we go to Radar, Interferometric, Products, Coherence Estimation. So we take as input the co-registered stack, and we leave everything as default in the Processing Parameters section, and then we select OK. We select Run. Here we have our coherence product. We can now close this window. Let's take a look. So if we double click on that, it'll open in a viewer. And here we have our coherence image. So you can see that areas with high coherence are white, which correspond mainly to built-up areas where there have not been so many random changes between the two image acquisitions. Whereas low coherence, you can see a lot of low coherence in surrounding areas. We will now go through the same processing chain that we carried out for the amplitude images. So we will do a deburst, a multi-looking, and a terrain correction. So first let's do the deburst. So radar, Sentinel-1 tops deburst. And here we select OK. And we select run. Then we do a multi-looking, radar multi-looking. And again, we leave the default range looks and azimuth looks in order to produce square pixels. Now we will do a terrain correction. So we go to geometric, terrain correction, range Doppler terrain correction. We select the multi-look product and we leave everything as default and we click on run. We can now close this window and here we have our final terrain corrected coherence image. So we can open this final image and see how it looks. What we now want to do is to use this coherence image as well as the amplitude images from the two image acquisitions, and we're going to try and map the urban areas with these three information layers. So we will keep only this final processed coherence image, and we will close all of the intermediate images. So we can do that by selecting the final terrain corrected coherence, right-clicking, and select close other products. Now we will open the two processed the sigma naught images. So here we go to the two terrain corrected sigma naught images. So here we have the two terrain corrected multi-look calibrated sigma naught images. And we have the coherence. And what we will do is we'll merge them together into a stack. So we go to radar, co-registration, stack tools, create stack. And here we will add opened to add all of the products. And we will leave everything as default here. And we click on and we select run. So here we have a stack with the coherence and the sigma naught backscatter of the two images. What we'll do is we'll create some additional bands, including the average of these two backscatter images and also the difference. But we'll do that with the images in decibel. So here we select linear 2 from dB, and we create two additional virtual bands in decibel. We will now save these as not just virtual bands, but we will save them to the file. So here we select convert band and convert band to each of these two virtual bands. Then we save the image. This way, when we process these images in decibel, we're not always processing the bands on the fly. We're actually processing the data that's written to a file. And it should speed up the processing. So what we will do here is we'll create the average of these two, and we'll also look at the difference between these two. Bear in mind that these are now in a logarithmic scale, and when you do a difference in logarithms, it's the equivalent of taking the logarithm of the ratio and vice versa. So to do that, we go to raster, bandmass, and here first we will select the mean, the average backscatter, and here we will deselect virtual to write the newly created band to file, and here we select edit expression, and here we will add the two backscatter bands together and divide them by 2. So here we have the mean dB, and we select OK. Now we will take the difference, so we will go to, again, to raster, bandmass, and here we will select, we will create a new band which we will call difference. Again, we will deselect virtual, and here we take one image and subtract the other image from it. And we select OK. So here we have these new bands, and what we'll now do is we will open an RGB composite with these new bands, and we will select in the 3 RGB channels, we will select in red the coherence image, in green the mean image, and in blue the difference image, and select OK. And here we have an RGB composite with the coherence, the mean and the difference. Now how do we interpret this image? The areas which are in red have low backscatter and high coherence. So these could correspond to agriculture or bare soil areas. The areas which are in yellow, on the other hand, have high backscatter and high coherence. So these areas could correspond to built-up areas. What we will now do is we'll try and mask out these built-up areas by creating a new mask layer. So we do that by selecting raster, bandmass, and here we can select a new band which we'll call urban footprint. And we'll create a new expression where we type in a conditional expression, and the conditional expression we can select from here, from the operators. And what we'll do is we'll put in some thresholds in the conditional expression which will help us mask out the urban areas. So first of all, we will select a condition on the average backscatter, on the mean backscatter. So here we will say if mean backscatter is greater than -10, and we will create a condition on the coherence. Here there's a slight bug. It does not appear where the cursor is, so we have to modify this a little bit. And coherence is greater than 0.6. Let's just put a space in between these two. Then the mask will equal 1. Otherwise, it will equal 0. So here we're going to mask out the yellow areas. and then we select OK. And these areas should correspond to urban areas. And then we select OK. And here we have our mask. We can compare this with the RGB image by selecting window tile evenly, ensuring that the cursor and the zoom are synchronized, and here we can compare the two images. We can also compare the two images by overlaying one on top of the other by selecting Layer Manager, selecting the plus icon, image of band, next, and here we select our mask and we select Finish. Now we can select this mask image and change the transparency to compare the two images. This mask may not be perfect. You can play around with the thresholds to improve the result. In this tutorial, we used two Sentinel-1 images in single complex format to mask out urban footprints. I hope you enjoyed the tutorial. Thank you for watching.